Hello everyone, welcome to our channel. This is Dinesh MA, working as Assistant Professor in the Department of Electronics and Communication Engineering, Maharaja Institute of Technology, Mysore. In the last session, we understood the open loop configuration of an op-amp. And in this session, we'll discuss some of the applications of an op-amp. The very first application we'll be learning is an inverting amplifier. So let us understand how an op-amp can be used as an inverting amplifier. And for the same, circuit is shown here. So here we can see the input signal source is represented as Vin, which is applied to the inverting terminal V2 through an input resistance R1. And the non-inverting terminal V1 has been connected to ground. And I1 is the current that is flowing through the input element R1, and this I1 cannot flow into the op-amp because of the high input impedance what the op-amp offers. We know that typically any op-amp will be having input resistance in mega ohms range, so this current cannot get into the op-amp. So this current will be flowing through the feedback path where we have the feedback element RF. Resistance RF is used as feedback element. So this current that flows through this feedback path shall be called as IF. So essentially this I1 is equal to IF. Now let us derive the expression for the output voltage of this inverting amplifier. So because of the KCL, we can say I1 is equal to IF. That is, the current that is flowing through the input element is same as the current that is flowing through the feedback element. Let us call this as equation 1, and I1 using Ohm's law, it can be written as Vin minus V2 divided by R1. So I1 is written as Vn minus V2 divided by R1, and here we have V2 which is virtually connected to V1 and V1 is connected to ground. So we can say V2 is approximately equal to V1, which is equal to 0. So I1 would be equal to Vin minus 0 divided by R1, which is Vin by R1. Let us call this as equation 2. And now let us derive the equation for IF. IF is the current that is flowing through the feedback path RF. Let us apply Ohm's law here too, so that IF is given by what? V2 minus V0 divided by RF, right? So let us write IF is equal to V2 minus V0 divided by RF. Again, what we have? V2 is approximately equal to Vin, which is equal to 0. So IF can be written as minus V0 divided by RF. Let this be equation 3. So now we have the expressions for I1 and IF, and let us substitute these two in equation 1. So 2 and 3, let us substitute this into equation 1, so that we can write Vin divided by R1 is equal to minus V0 divided by RF, and V0 will be given by minus RF by R1 into Vin. So this is the expression for output voltage. And the same thing can also be written as V0 is equal to minus A into Vn, where A represents the closed loop voltage gain which is given by RF by R1. So by varying the values of the feedback element and the input element, we can achieve whatever the gain we want. So here there is a negative sign in the output equation which represents the output voltage will be 180° out of phase with respect to input. So if we draw the waveforms, let us say this is the input voltage signal that has been applied, and this is on time scale. So let us draw the output waveform. So output waveform should be looking like this. So here what we can see is when the input signal has got positive cycle, output will be having negative cycle. When input has got negative cycle, output will be having positive cycle. So this is going to be repeated. So even this is also on the time scale. So what we can see here in the output waveform is, or in these waveforms is, the output is 180° out of phase with amplified level, right? So that is given by the ratio RF by R1. So this is the working of the inverting amplifier. Now let us understand the working of non-inverting amplifier. As we can see here in the circuit diagram, the input signal Vin is applied to the non-inverting input terminal V1 and the inverting terminal V2 has been grounded. The current I1 is flowing through R1 and this cannot get into op-amp because of the high input impedance. So this current I1 will be flowing through the feedback element RF as IF. So I1 is equal to IF. So let us equate I1 to IF and consider this as equation 1, and by using Ohm's law we can write the equations for currents I1 and IF, and later we'll equate these two. Now I1 is given by 0 minus V2, 0 minus V2 by R1, 0 minus V2 by R1. Because of the virtual connection concept, V2 is approximately equal to V1, which is equal to Vin. V2 is approximately equal to V1, which is equal to Vin. So I1 can be written as minus Vin divided by R1. And let us consider this as equation 2. Now again applying Ohm's law for this path, we will consider the value for IF. So IF is given by V2 minus V0 divided by RF, V2 minus V0 divided by RF. Again we have the value for V2 as Vin from this equation. So IF can be written as Vin minus V0 divided by RF. So let us consider this as equation 3. Now let us substitute equation 2 and equation 3 in equation 1. That is minus Vin by R1 equals to Vin minus V0 divided by RF. So with this we will find out the equation for V0. So this can be written as minus RF, sending this to the numerator, minus RF by R1 into Vin is equal to Vin minus V0, so that V0 is equal to Vin plus, sending this whole term to the other side, So this is what we have. So V naught can be finally written as V in into 1 plus Rf by R1. So this is the expression for the output voltage of a non-inverting amplifier using op-amp. So this can also be written as V naught is equal to V in into A, where A represents the closed loop gain and is given by 1 plus Rf by R1. And from this equation, what we can understand is the output voltage will be in phase with the input voltage signal with the gain 1 plus Rf by R1. So the gain can be varied by using the feedback element and the input element Rf and R1 respectively. So the output voltage waveform would look like this. So from this, what we can understand is the output signal is in phase with the input signal with an amplified level. So this is the working of non-inverting amplifier using op-amp. Now we will understand the working of a summing amplifier. This summing amplifier can also be used as scaling amplifier and also as averaging amplifier. Now we have three voltage sources VA, VB and VC, and these are connected to the inverting terminal V2 through input elements RA, RB and RC respectively. And as we can see here in the circuit, we have current IA that is flowing through RA, IB is the current that is flowing through RB and IC is the current that is flowing through RC. And by Kirchhoff's current law, we can say the current that is coming into the terminal V2 through this input terminal is the algebraic sum of IA, IB and IC. And this total current cannot get into op-amp because of the high input impedance, and this will be flowing through RF as IF. So what we can say is the algebraic sum of IA, IB and IC is equal to IF. So let us get into the derivation of the output voltage equation. So let us say IA plus IB plus IC is equal to IF, and let us call this as equation 1. Now by using Ohm's law, we can say IA is equal to VA minus V2 divided by RA, IB is equal to VB minus V2 divided by RB, and IC is equal to VC minus V2 divided by RC. So IA is equal to VA minus V2 divided by RA IB is equal to VB minus V2 divided by RB, IC is equal to VC minus V2 divided by RC. And we know that V2 is virtually connected to V1 and V1 is connected to ground. So virtually V2 is connected to ground potential. V2 is approximately equal to V1, which is equal to 0. So IA is equal to VA by RA IB is equal to VB by RB and IC is equal to VC by RC. So now we have substitutions for IA, IB and IC, and let us know what is the substitution for IF in this equation. So IF is equal to what? V2 minus V0 divided by RF by Ohm's law. So V2 minus V0 divided by RF, and we know V2 is approximately equal to V1, which is equal to 0. So IF is equal to minus V0 divided by RF. So now what we'll do is we'll substitute the value for IA, IB, IC and IF in equation 1. So equation 1 will become VA by RA plus VB by RB plus VC by RC equals to minus V0 by RF. So now the equation for V0 can be written as, transferring this minus sign to the opposite end and also RF as well, this can be written as minus RF by RA into VA plus RF by RB into VB plus RF by RC into VC. So here we have an expression for V0 which is equal to minus RF by RA into VA plus RF by RB into VB plus RF by RC into VC. Now depending on the values of RF by RA, RF by RB and RF by RC, a portion of VA, VB, VC will be considered for the summation of V0. So with this, different values for RA, RB, RC and RF, this circuit can work as scaling amplifier. So this is the expression what we have for scaling amplifier. Now in this equation, if the values what we have for RF, RA, RB, RC, if I consider if RA is equal to RB is equal to RC is equal to R, then V0 can be written as minus RF by R, because RA, RB, RC is equal to R, we can write these values as common out and make this as this. So this is another function what we have for the same circuit. So what we can see here is RF by R into VA plus VB plus VC with the negative sign, and with this equation makes this circuit to work as an averaging amplifier by selecting the appropriate value. By making RF by R is equal to 1 by 3, so this circuit works as an averaging amplifier. Now in the same equation, if we equate all the resistance values, let us say if RA is equal to RB is equal to RC is equal to RF equals to R, then V0 will be equal to, here if RF is equal to R, then this cancels, then what we have is minus of VA plus VB plus VC. So here what we can see is this op-amp circuit, if all the resistance values, the input resistance values and the feedback resistance values are equated, then the op-amp will be working as summing amplifier with negative sign. So this is the expression for the summing amplifier. So we have this negative sign in all the equations because the op-amp is connected in inverting mode. So we have the negative sign. So this is the working of an op-amp circuit as an summing amplifier, scaling amplifier and averaging amplifier. So that's all what we have for this session. So in this session we have understood three applications of op-amp. One is inverting, second one is non-inverting, and the third one is summing amplifier, which can also be used as averaging amplifier and scaling amplifier. In the next session, we'll discuss some more applications of op-amp. Thank you.